when she was at Microsoft Research India also. So I know Shruti for a long time. And Shruti is a PhD student at Carnegie Mellon University. And I think her advisor is Graham Newbeck, if I'm right.
Yep, that's right.
Yeah, and her primary research interest is multilingual natural language processing with focus on low resource and endangered languages. I think she has worked a lot on code switching also. You can check out that work. And obviously her research is great, and she is supported by Bloomberg Data Science PhD fellowship. Much of our work in PhD is focused on name entity recognition and name entity linking for low resource languages, which she will talk today. So before wasting any more time, I'll let Shruti to talk about the awesome work. That's all.
Okay, hi everyone. Thanks for the really nice introduction, Vivek. I'm Shruti, and I'm a PhD student at Carnegie Mellon University. I'm in the Language Technologies Institute, which primarily has people focused on natural language processing and other related fields. So today I will be talking about some of my work with many collaborators, of course, on entity linking for low resource languages. I'm happy to take questions. So I plan for the talk to be about 40 minutes, might be shorter if I go fast, but I'm happy to take questions in between the talk as well. So just since there are just a few of us, just turn on your video and interrupt me, and I'll be happy to answer questions at any slide. I'm going to be talking about 3 papers that were recently published or accepted to be published. So the first paper is on creating an entity linking method for low resource languages. The second paper basically takes the first method as a baseline and tries to improve upon it and show substantial improvement for several low resource languages. And finally, I show how we can use information from these entity linking methods that are specifically designed for low resource languages and improve named entity recognition in a limited data scenario. So I'll get started, and thank you all again for attending the talk. So let me see. Okay, there we go. So the first thing I'm going to talk about is a method that we call pivot-based entity linking, and we applied this to low resource languages, and this was published last year at the AAAI conference. So first, I'll introduce the task of entity linking, just for a little bit of familiarity and context before we dive into the actual method that I want to present. So entity linking, so as we all know, natural language contains entities like person names and organization names, location names. So entity linking is essentially the task of associating these named entities with their corresponding entries in some knowledge base like Wikipedia, for example. So consider this sentence that we have that has 2 named entities. So the goal of entity linking is to identify the appropriate Wikipedia entry for each of these named entities. So having structured information from Wikipedia is useful for downstream applications, including document understanding, event coreference, and information retrieval. So cross-lingual entity linking involves linking entities from one language to a knowledge base that is in another language. For example, consider the same entities, Hawaii and the United States, in 2 languages, Javanese and Marathi, and we want to link them, as before, to English Wikipedia. So basically, we're trying to go from one language to a knowledge base in another language. So the entity linking pipeline typically consists of 2 steps. So the first is, given an input named entity like the US, the first step is candidate retrieval, where the algorithm retrieves a short list of knowledge base entries, which are potential candidates for the given input mention. The second step is disambiguation, where a sophisticated disambiguation model takes the short list of entities and tries to identify the correct entity link from the short list. So why split this into 2 steps? This is primarily because the knowledge base is usually very large and has millions of entries. Like English Wikipedia, for example, has over 5 million entries. And disambiguation algorithms are too computationally expensive to run on all 5 million entries. So we have a quick candidate retrieval to get a short list and then do a more sophisticated disambiguation. So when we have monolingual entity linking, like when we're going from English to an English knowledge base, string lookup is a very common way to get a short list of candidates. So in this work, we're going to focus on the candidate retrieval problem, specifically in the cross-lingual setting, not in the monolingual setting. So existing methods for cross-lingual candidate retrieval attempt to translate the entity from the source language to the language of the knowledge base. So for example, translating an input entity from Javanese to English, which could be the language of your knowledge base. And in order to construct a word-by-word translation lexicon, Wikipedia language links are often used by existing methods to basically translate the entities. So around 300 languages do have Wikipedia, and this makes it a useful source for creating lexicons. And some languages like Swedish and German, large lexicons with high coverage can be created because they have millions of links. However, for lower resourced languages like Tigrinya and Lao, far fewer links are present, and it's difficult to get a high coverage lexicon to do accurate translation. Further, we know that there are over 7,000 living languages in the world, and Wikipedia doesn't exist for most of these. So how do we perform cross-lingual entity linking using existing methods when Wikipedia just doesn't exist? So in this work, we propose a method that doesn't rely on any bilingual resources in the source language for training. So instead, we leverage information and data from high resource languages for training the entity linking model. And then we transfer these models to low resource languages in a zero-shot manner. That is, we don't use any fine-tuning or joint training while doing the transfer. So first, I'll introduce our entity linking model. So in most existing work, English Wikipedia has been used as the target knowledge base, and that's what we will be using as well. So the primary goal is to identify the English Wikipedia article that maximizes some scoring function with respect to the input named entity. So since we don't have any training data in the source low resource language, we instead train a model to perform cross-lingual entity linking between some high resource language and English. So we use two character level LSTMs. One to encode entities from the high resource language, and the other to encode entities in English. And we calculate the cosine similarity between the two vector representations as a metric to score the English English knowledge base entries. In order to train the model, we use parallel entities between the high resource language and English. And for high resource languages, these are easily available from Wikipedia language links, for example, or other bilingual lexica. So for example, we could, a training sample could be the United States in Indonesian and English, and that could be used for training the model. Since we are effectively trying to rank knowledge base entries for linking, we use a max margin loss with negative sampling as our training objective. So this forces the cosine similarity with the correct knowledge base entry to be a certain margin apart at least from the score with an incorrect knowledge base entry. So the first thing we do in order to use our model with a low resource language is zero-shot transfer. So consider an input entity in a relatively lower resource language, Javanese. We simply encode this entity using the LSTM that is trained on the high resource language. So for example, we could use an LSTM trained on Indonesian. If the high resource language that we use for training and the low resource language in the test set are closely related, the transfer can potentially succeed. And close relatedness can be being from the same language family like Thai and Lao, and using the same script like Hindi and Marathi or Indonesian and Javanese. Second, we introduce the concept of pivoting with data in the higher resource language. So instead of scoring English entities to find the best knowledge base link, we instead calculate a similarity score with the parallel entity in a closely related high resource language. And the intuition behind this is that if the languages are closely related, it's likely easier to link to the high resource language rather than to link directly to English. However, our end goal still remains linking to the English knowledge base. But since we have lexicons in the high resource language, so bilingual lexicons between the high resource language and English, we can obtain the English entity quite easily. Therefore, we use the high resource language as an intermediate between the low resource language and English. For example, we link a Javanese input named entity to an Indonesian entity rather than linking directly to the English knowledge base entry. So how does this look with our model? We essentially encode both the input named entity in the low resource language and the candidate high resource entity with the same trained LSTM, which has been trained on the high resource language, and then calculate the cosine similarity between the vector representations of these two inputs. Overall, our method, the pivot-based entity linking, attempts to find the highest scoring knowledge base entry by calculating similarity with the English knowledge base entry itself, as well as with the parallel entity in a high resource language. It involves zero-shot transfer for encoding the low resource language entity mentioned, and it also involves pivoting with the high resource language. We also calculate the similarity with the English entry, because the low resource entity might either be close to the English entry, or in some cases, the corresponding high resource entity doesn't exist on Wikipedia, and then we can't do pivoting in those cases. So the final score for a particular knowledge base entry is the maximum similarity score, either directly to English or pivoting through the high resource language. Finally,
I have a question in the previous slide.
Mm-hmm.
Can you?
Yeah.
Yes. So you are pivoting the low resource language with the high resource language, which lie in the same language tree close to each other,
Mm-hmm.
and then you are also pivoting English with the low resource languages.
Mm-hmm.
What was the intuition behind these two pivoting? Why don't you pivot it like the English with the high resource language? Like, what was the reason behind it? Like, why?
Okay, so
Why do you just choose these two pairs, like these pairs, like?
Okay, that's a good question. So basically, the input, what we want to get is the corresponding English knowledge base entry for the low resource language mention. So,
Yes.
so we have a bunch of candidate English entries in the knowledge base. And for some of those candidate entries, we also have the parallel high resource knowledge base entry in a different language. Okay. So we have the input, and we have two sources of comparison, one in English and one in the high resource language.
Okay.
So we're basically going to compare the input named entity, which is in a low resource language, with all the knowledge base entries in English and all the knowledge base entries in the high resource language.
Okay. So the HRL is acting as a pivot, so the title makes sense. Okay.
Exactly. So, and because we have a mapping between the HRL and English, so we can easily get the English knowledge base entry. But we don't have a mapping between the low resource language and the high resource language, and we don't have a mapping between low resource language and English. So the only mapping we have is between high resource and English.
High resource and English. Okay.
Yeah. So that's why we compare to these, because they can be mapped to each other.
Okay. Thanks.
Yeah. Okay, so finally, we noticed that although languages may be very closely related, either through the same language family or typologically, they could use different alphabets or writing systems. And in this case, the character LSTMs won't transfer. So instead, we propose converting all data to the phonological space using the International Phonetic Alphabet. This is an alphabet which is language universal and essentially represents how words are pronounced. For example, Thai and Lao are very closely related languages and are in the same language family, but they use different scripts. So we can't do zero-shot transfer in this case. However, if we train and test the model by converting all the data into IPA, we can see that entities are actually pronounced quite similarly in both these languages, and zero-shot transfer can potentially succeed. So for our first set of experiments, we trained models on 53 high-resource languages that can potentially be used for transfer. Our test set contains 9 low-resource test languages, which are listed here. So as you can see, these languages all use different scripts and come from several language families from around the world. The test set contains parallel article titles from Wikipedia, and we use English Wikipedia as our target knowledge base. So we train all our models on the high resource language data, and we use the low resource languages only as test data. So the first baseline is a translation-based baseline, as previous work has used. We can see the entity linking accuracy of the translation model here. So this uses a bilingual lexicon in order to translate the entity and get the entity link. We also compare to the encoder model described earlier, using only the similarity to English without any pivoting through the high resource language. We can see that using the character level LSTM improves the accuracy quite a bit as compared to the translation baseline. For pivoting, we use 2 experimental settings. So the first is when we manually select a single pivot language based on our prior knowledge of language families and linguistic properties. So we see that this performs much better than the 2 baselines, showing the importance of pivoting through the high resource language when we have that data available. Finally, we use multiple pivot languages where we attempt to transfer from all 53 pivot languages, and this gives a small improvement in accuracy. Next, we conduct—
I have a question.
Sure.
Last slide.
Yeah.
So when you did the multiple, you choose all the languages, despite if they are connected or not.
Yes. So we chose, we basically just took all the scores from all the languages and ranked them together, and then picked the highest one and saw if that was the correct entity or not in order to compute the accuracy.
Okay, and this will not hurt performance because you are just doing similarity and comparison of linking between the languages. Okay.
Right. Interestingly, it does hurt performance for 1 or 2 languages, but
okay.
And you can see the paper for per language details, but on average, it's slightly better than using just one language.
Interesting. Okay, thanks.
Yeah, good question. Thank you. Okay, so next we conduct experiments on full documents from news sources, blogs, and social media for 2 low-resourced Ethiopian languages, Tigrinya and Oromo. So we compare to both the encoder and the translate baselines and use a manually selected pivot, Amharic for Tigrinya and Somali for Oromo. So as you can see in the graph, the entity linking accuracy does improve with the pivoting method. We see that the supervised translation method doesn't work very well because the Wikipedia size for both these languages is very small. We see that pivoting works better for Tigrinya than for Oromo, and this reflects the fact that a closely related pivot language is necessary for the success of our method. So Amharic and Tigrinya are much more closely related than Somali and Oromo in terms of linguistic properties, and that's reflected in the success of the pivoting method. So next, we analyze the utility of the proposed phonological transfer method. So, and this is, we use this when the source and the high resource language have different scripts. So we can see that orthographic transfer, so when we don't convert to IPA, when we stay in the same orthography, so orthographic transfer works better if the script is the same as compared to when we convert to IPA, but not by too much. But we see that sticking to the original script completely fails when the scripts are different. And this makes sense because character level LSTMs can't transfer across different scripts. And we see that using the phonological representation leads to much better zero-shot transfer across different scripts. So as part of our analysis, we also try to see whether if we add a small number of samples from the source language itself, does that improve performance over just doing a zero-shot transfer? So in the graph, we can see how the performance changes when we add a fixed number of samples to the training set and train in conjunction with the high resource language. So we can see there are languages that are very similar. So for example, Javanese and Indonesian or Hindi and Marathi don't actually show that much improvement when we add data from the source language itself. So it's able to get most of the information it needs just from the transfer language. But for the models that use phonological transfer, we see much more improvement when we add some data from the source low resource language. Finally, we look at, so far we've only been looking at the top one candidate to see whether it's accurate or not. But the main application of our system would be for candidate retrieval to basically shortlist a small number of candidates from the large knowledge base. So in this graph, we can see the candidate recall up to looking at up to the top 100 candidates. We see that in a lot of cases, the highest scoring candidate is actually the most accurate. For example, in Javanese and Indonesian and Tigrinya and Oromo. However, for some lower scoring languages, we see that if we add more candidates going up to the top 100 candidates, we can actually provide a downstream disambiguation model with more improvement headroom to disambiguate between the top 100 candidates rather than just select the top one candidate. So finally, just to summarize, we presented PBEL, which is an entity linking method that leverages high resource languages for zero-shot transfer. And we saw an average improvement of 17% over the baseline systems. The phonological transfer improves pivoting by 36% on average for dissimilar scripts. Next, we ask whether we can do better than this specifically for low resource candidate retrieval. So the next thing I'm going to present is pivot-based entity linking plus, which tries to improve on the method that I just presented. And this is with my collaborator, Shuyan, who is also a student at Carnegie Mellon. And this paper will be presented at ACL next week and was published in the Transactions of the ACL journal this year.
So, I have a question before moving this,
sure.
if you mind. Okay.
Yeah.
So some questions in general I have. So first of all, like in this, I like the fact like which you observe that if there were similar languages, you don't get improvement.
Mm-hmm.
Which somewhat also say something about like it's what your thought like about these pre-trained language models. Do they only work for languages which are like somewhat similar kind of thing, like, or like, do you have any thought about that? Like, how does the pre-trained model like MBERT and all fit in this context? Because I feel like what you discover is somewhat relevant to that also, and also, yeah,
that's a good question. We did not really explore using BERT for any of these languages because BERT is not trained on any of these low resource languages. So BERT is trained, MBERT is trained on the top 100 languages in Wikipedia, and none of these low resource languages even fall in the top 100 on Wikipedia. Yeah. So that's the primary reason we haven't tried BERT on this yet. Of course, there is the argument that since BERT works at the subword level, it could potentially work for these languages, but we haven't tried that yet. So I don't have an intuition on how well BERT will work for entity linking on low resource.
Okay, one more question. So when you say like, so one is like you find manually which language street belongs to, which is close.
Yeah.
And other is, or you train on all 54, whatever the language set you have pivoting.
Yeah.
So I'm assuming that computationally that would be very expensive. So is there like any ways like we can find, okay, this is my language. For example, I'm a new person and I want to train some model for a language. Like example, like I'm a data scientist and I joined a new company and they give me this problem. So instead of like, and I have limited resources. So is there any way I can find which language is better for me, despite like going over all of them one by one or training on all of them?
Okay, that's that's a great question. There was another paper from our lab on this actual topic, and they in fact used this system, the pivot-based entity linking, as one of their cases. So you can look at that paper. It was published at ACL last year, and basically they tried to predict which is the best transfer language given a source language. So and it actually worked pretty well. So so I think that would be like a good indication. Like if you could use that system, that would be a good indication as to which language or few languages you could train the model on, instead of doing all 53 or 100 or whatever.
Yeah, I will get back to you after the talk for that paper.
Oh yeah,
Thanks
sure. I'll send the link as soon as
sure.
as soon as the talk is done.
Yeah, sure. Thanks a lot.
Yeah. Okay. Are there any other questions?
Anyone who has question, then unmute and ask. I don't know.
Okay, gonna take that as a no. So so yeah, I'll continue and talk about some improvements we've made to the pivoting system, and basically compare it to the pivoting system and see what exactly improved and where. So here we go. Right. So this work basically starts from a systematic analysis of the failures of the pivoting-based entity linking system. So we randomly selected 100 samples from 4 low resource languages, run it through the pivoting system, and then manually annotated the error types. So we mainly discovered 4 types of mentions that caused errors. So here we have an example in Marathi, and it's corresponding knowledge base entry. So Marathi is a relatively lower resourced Indian language. So the first type of error we noticed is what we call a direct error. And these are just simple cases where there is a word-by-word mapping between the input named entity and the knowledge base, but the method was still not able to get this correctly. The second is alias errors, and this is where the input named entity is actually very different from the knowledge base name, but they actually refer to the same entity in the real world. So for example, here the Wikipedia page name for the actress Kobe Smulders, the title is Kobe Smulders, but the actress's full name is Jacoba Francisca Maria Smulders, and it's very difficult for the model to be able to link these because they're so different. The next type of error that we noticed is a translation error. So for example, Carnegie Mellon University in Marathi, so Carnegie Mellon is transliterated, but the word university is translated. So you can see the IPA, the pronunciation written on this slide. You can see that the word university is not written as university in the input mention. So this is also challenging for the model to learn. Finally, we observed that there are sometimes extra words on either the knowledge base side in English or on the low resource side in the named entity mention. So, oh, sorry. So we created 3 classes for the rank of where the correct entity lies in the top 30 candidate list as retrieved by the pivot-based entity linking system. And this is the distribution for each of the error types. So the light blue portion of the graph means that the correct entity is the top 1 candidate and the prediction is successful and a downstream disambiguation model is not necessary. So, and the darker blue represents when the correct entity is in the top 30 candidate list, but is not the top entity. But if the top 30 candidate list was used in a downstream disambiguation model, it's likely that the correct entity would be picked up. Finally, we see that a large number of entities are not even in the top 30 list, which makes it impossible for the downstream disambiguation model to recover. So we see that the baseline pivot-based entity linking system fails quite a bit even on the direct word-by-word mapping cases. And as shown in the green portions, a large number of correct entities were outside the short candidate list across all the error types, and this strongly limits the end-to-end entity linking performance. So
I have a silly question, but
oh yeah, sure,
yeah,
go ahead.
So why did it 30 was any reason behind?
30 is actually the standard that's used in many entity papers in the past. So we just compare to in the experiments we compare to those. So that's why we picked 30.
Okay, got it. Thanks.
So based on our analysis, we proposed 3 improvements to fix the problems in the baseline method. So the first is we noticed that there is a gap between the training data and the test data. So as you can see, the training data mostly has entities that have word-by-word mappings. So if you look at the entities that are highlighted, Kobe Smulders in Hindi and Kobe Smulders in English are used as training pairs. And these have word-by-word mappings. But while evaluation in a low resource language, say Marathi, for example, we could only get the last name Smulders as an input, and we still should be able to map it to the correct knowledge base entry. But such mappings don't exist in the training data at all. So we just propose a very simple method to extract these mention entity mappings from Wikipedia for the high resource language. So we still don't use any data from the low resource language, but we collect them from the high resource language Wikipedia and add them to the training data. And while this is perhaps obvious, this in hindsight, this method hasn't been used before. And that's why there's this big discrepancy between the training and test sets. So once we add this, we actually do see some improvement on the entity linking accuracy. The next thing we do is that we know it's very hard for a string matching model to know that 2 very distinct strings actually refer to the same entity. So for example, the actress's full name only has one word overlap with the name, with the short name on the Wikipedia article. So luckily we have Wikidata, which is a large-scale encyclopedia that has already collected a large number of aliases in English. So here are the aliases for the actress Kobe Smulders, and the actress's full name is part of this list. So using this additional data in English, we during test time, we also calculate the similarity score between the input low resource mention and the English aliases. So for a specific knowledge base entry in English, the maximum score across all the aliases serves as the final similarity score. So the third improvement that we propose is that we know the baseline model sometimes doesn't perform well on simple word-by-word mapping cases where the entity and the input entity mention and the knowledge base entry have a one-to-one mapping in terms of words. And this indicates that perhaps the character level by LSTM is not learning a very strong representation of the string, especially from the limited training data that we have. So we propose using character-based n-gram encoders called Caragram. This has been used in previous work as well from 2016. So this model treats an input string as a bag of n-grams and finds the embedding for each of these n-grams in a lookup table. So these are neural embeddings which are trained with the model. And the final embedding for this string is the sum of all the embeddings for all the n-grams followed by a nonlinear activation function. So overall, the Caragram method provides a more direct and explicit way to encode strings as compared to the character level by LSTM.
I have a question.
Yeah.
So how did you train this? Like, do you have original embedding? That's how you like propagate this loss?
No, so this is all trained on a high resource language. So okay. It's trained, we just replace the character level LSTM with this model.
Oh, okay. Yeah. So it's end-to-end. Okay.
Yes, yes. But we don't use any low resource data. We just rely on the similarity between the languages to transfer to the low resource language.
Okay. So my doubt was mainly like because the subwords will be shared across other similar entity also. So that was, I was thinking like, how did you, but I think when you train end-to-end, it's work well.
Yeah. Cool. So our experiments cover 7 languages. So 4 of them are from the DARPA Lorelei project, Tigrinya, Oromo, Kinyarwanda, and Sinhala. 2 of which we already did experiments with in the previous paper. And then when we were working on this paper, they released 2 more data sets. So we used that as well. We also use 3 languages from Wikipedia datasets that are publicly available, Marathi, Lao, and Telugu. So all of these are pretty low resource languages. So these are the sizes on Wikipedia, as you can see, at least compared to English, which has like 5 million articles. These are much smaller in size. So we compared to 2 baselines. So the first is the WikiMention baseline, the performance of which is shown here. So WikiMention is essentially gets supervision from the source language Wikipedia, and that's why we didn't test it on the Wikidata for a fair comparison. So WikiMention is essentially the method that uses translations to convert the low resource entity to its English equivalent, English translation. So so the performance is shown here. And the second baseline is the pivot-based entity linking method that I just presented a few slides ago. So with our 3 improvements, we see that the PBEL plus method actually improves over PBEL on 6 of the 7 languages. And we also see that without any access to resources, it outperforms the supervised WikiMention method on 3 languages. It doesn't outperform the method on Sinhalab, whose Wikipedia size is relatively larger than the other 3 languages. So we also look at the error distribution with the same samples that we used previously to evaluate the failures of the PBEL system. So we can see that a large number of errors are eliminated, and a more number of entities have the correct entity link in the top 1. As the top 1 candidate. So we see significant gains on both the direct and the alias types of errors. We also see that the downstream disambiguation model has a larger headroom for improvement with the darker blue section of the graph. And a number of translation errors are also resolved as a side benefit. So to investigate how the candidate generation model influences an end-to-end system, we use the candidate lists retrieved and pass it to a disambiguation model. The disambiguation model is also a 0-shot model. It's an existing model. It doesn't use any extra resources in the low resource language. So we can see that the PBEL plus method improves the end-to-end accuracy over just the PBEL method in all the languages. And we also see that there's more improvement headroom for the downstream disambiguation system. So if we used a more sophisticated model, we could get even better accuracy with these candidates. So in summary, the systematic analysis that we did over the pivot-based entity linking system led us to developing 3 methods to handle the diverse realizations of an entity mention and the unique identification of an entity, as well as using a better modeling strategy for strings. And with these improvements, we see an average gain of 16.9% in gold candidate recall for entity linking and 7.9% in end-to-end entity linking accuracy. So, so yeah, that's the end of this work. Does anyone have any questions before I go to the last one? Okay.
Just a general doubt.
Yeah.
Can many things which you mentioned in the pipeline, like the improvements, basically. I feel many of them would be even affected when you do entity linking for a high resource language also. Or do you think these improvements are not that good, or they are not needed or something? Have you ever thought of that?
That's a good question. So for high resource languages, the translation method actually works really well because the translation lexicons have very high coverage. So these improvements are probably not going to help that much. So the baseline that we used, WikiMention, which is the translation method, that works really well for high resource languages.
Okay, that's why I think in one of the thing which has high resource, it didn't work. But
yeah,
okay, good.
Exactly. Yeah.
Yeah, thanks.
Yeah. Okay, so I'll move on to the last one. So this is it's going to be a little short. It's based on a short paper, and we can wrap up after that. And happy to take more questions. So as we know, we looked at the candidate retrieval system for low resource languages. Given an input mention, we get candidates and then give it to a disambiguation model to select the best candidate. But where do we get the input mentions from? So the mentions are actually extracted from natural language text using named entity recognition. And in all of the previous work, we just assumed that we had the correct entities extracted. But this is obviously not a realistic case because entities are not extracted from natural language text always. So finally, I would like to present our work on using information from the entity linking system that we just discussed to improve low resource named entity recognition. And this is going to be presented at ACL next week. So if any of you are attending, feel free to watch the video and come to the QA session and so on. So named entity recognition is the task of identifying named entity recognition in named entities and their types. So if you see this example, Mark Watney visited Mars. So we want to detect the person type and the location type as well as the span of the entity. So the F1 scores, which is the metric used for measuring named entity recognition performance for English, are over 93%. But they are much lower for low resource languages. And one of the main reasons is that the number of labeled sentences in low resource data sets is much less than even 10% of English data sets. So what we want to do here is, can we use data from English knowledge bases like Wikipedia as supplemental information to improve low resource NER? So before the widespread adoption of neural networks in natural language processing, named entity recognition systems used linguistic features such as lexical and syntactic features to improve performance. With neural networks, these mostly became obsolete because neural networks don't need these features to get strong performance. But recently, it has been shown that integrating both the approaches, so integrating handcrafted features with neural models, is useful for named entity recognition on English text. So of specific interest to us are the linguistic features based on large lists of entities called gazetteers. So these are constructed by looking up the input string in the gazetteer and then forming binary valued features based on whether or not the string is found in the list of entities or not, as well as the type of the entity that has been found. So like location, person, or organization. So this is the standard method of creating gazetteer features that has been used in past work over many decades and was very important especially for non-neural models. So using additional information from gazetteers does have the potential to improve low resource NER, but there are several challenges to simply adopting the existing gazetteer methods. So specifically, existing gazetteers in low resource languages are very limited in their coverage. So we already saw some examples of this where Wikipedia, which is often used to collect these gazetteers, has 2 million named entities in English, but far fewer named entities in low resource languages like Kinyarwanda, Oromo, and Tigrinya. So expanding gazetteers is both time consuming and expensive. And additionally, finding enough annotators is difficult for some low resource languages. So as an alternative, we present soft gazetteer features. So these features don't rely on large entity lists in the target language. Instead, they are constructed using the information from English knowledge bases such as Wikipedia or Freebase. And of course, to get this information, we use entity linking, as that's the most common way to extract this information. So from the entity linking model, we get a list of candidates, as we saw, as well as with their similarity scores. So the candidates are from Wikipedia or some other English knowledge base, and they also have types, so like location, organization, etc., and much more information. You can see an example of a candidate list here with their scores. If the input is Chicago, you have the top candidate, which is likely Chicago, the city, with the highest score, and other entities named Chicago with lower scores. So given an input sentence, the knowledge base entries are retrieved for each span in the input sentence, and the scores from the candidates are used to create soft gazetteer features and then applied to each word in the span. So consider a feature that represents the top scoring knowledge base entry. So it's the knowledge base entry that's retrieved with the highest similarity score. So given a sentence such as this one in the low resource language Kinyarwanda, we use entity linking to obtain a list of knowledge base entries with their scores and their entity type. So like location, for example. Using the scores, we create the soft gazetteer features for the whole span. And these features are continuous valued as opposed to the traditional binary valued gazetteer features. And these are based on the entity type of the knowledge base candidate. So the feature vector for the span is then applied to each word in the span as shown in the figure. So the vector is applied differently depending on whether the word is the first word in the span or not. And this reflects the BIO tagging scheme that's commonly used for named entity labeling. So similar to the features representing the top scoring candidate, we additionally use features that represent the top 3 candidate scores, the type-wise counts of the top 3 candidates, the type-wise counts of the top 30 candidates, and the margins between the scores of the top 4 candidates. And the vectors for each type of feature are concatenated and normalized to form the final soft gazetteer features for each word. So we use the BI-LSTM CRF architecture as our base model. This is a model that's commonly used in state-of-the-art named entity recognition systems. So the BI-LSTM encodes the input text, and the conditional random field, or CRF, makes a globally normalized prediction of tags over the sequence. So the soft gazetteer features are incorporated in 2 ways. So first, they are concatenated to the character representation and the word embeddings at each token of the input text. So this concatenated representation is then used as input to the BI-LSTM. Second, they are used as input features to the CRF. Additionally, we add an autoencoder to reconstruct the soft gazetteer features from the hidden state of the BI-LSTM. So the autoencoder reconstruction loss is added to the training objective, and this encourages the BI-LSTM to retain information from the soft gazetteer features. So the entity linking methods we use are similar to the ones that I discussed in the previous experiment setup. So additionally, we use exact match of Wikipedia titles from the target language or a related high resource language. We use WikiMention, which has the word level and phrase level translation. And we use pivot-based entity linking with the additional improvements. So we conduct experiments on 4 low resource languages: Kinyarwanda, Oromo, Sinhala, and Tigrinya. So the annotated data sets for named entity recognition in these languages are very low resource, merely 4 to 13% the size of the standard Connell 2003 English data set. So we compare the soft gazetteer method to 2 baselines. So the first is a BI-LSTM CRF model with no gazetteer features, and the average F1 score over the 4 languages in our data set is represented in the graph. We also compare to the existing method of creating binary valued features, and we see that this actually improves the F1 score over the model that uses no features at all. Finally, we see that the soft gazetteer features created using information from the knowledge base has the best overall NER performance. So next, we analyze what types of named entities actually benefit from the addition of the soft gazetteer features. We compare the recall of these entities between the baseline and the soft gazetteer method. So first, we expect entities that have a valid corresponding entry in the knowledge base to benefit from the additional information obtained through entity linking. We also look at mentions that are unseen in the training set, but are in the test set. In the figure, we see that the recall for both these types of entities increases when using the soft gazetteer features. So to summarize, the soft gazetteer method does not rely on high coverage entity lists to create gazetteer features for NER, and it improves NER over the baselines on 4 low resource languages. And in the future, we'd like to explore more sophisticated feature design and combining different entity linking methods. So in conclusion, we presented a method for candidate retrieval in the cross-lingual entity linking setting, and the method required no bilingual resources in the source language. We presented data and modeling improvements to increase the accuracy of the candidate retrieval. And finally, we used the improved candidate retrieval method as supplementary information to low resource NER models. And yeah, that's the end of my talk. And thank you so much for attending, and happy to take questions.
Thanks, Shruti. It was a wonderful talk. And I also like the way you summarize three connected work together in one presentation. That's pretty awesome. If anybody has question, please ask. I don't know why people are too shy. Okay, Mathia is there. Okay, go ahead.
Yeah, I have a question. So this system works with a low, well, these systems, all the ideas you presented today, they work with a low resource language, right? And then like a high resource language that is, according to what I understood, is similar. I mean, has linguistically similarities among, let's say, there are among the same family of languages, and that one is a high resource one that can be compared to English in this case, right?
That's correct. Yes.
Okay.
Yes.
So I don't know if you mentioned this, or maybe I missed that or something, but so how important is this? How related are these two languages? The one that is low resource and that other one that is similar. How important is that similarity for the final outcome? I don't know if that makes sense. The question makes sense.
Oh yeah, it's a great question, and I think that in our experiments we saw that it's actually very important that the languages are closely related, and the transfer does not, the zero-shot transfer of the model does not work when the languages are not related at all. So it is very important to have a close relation between the high resource language and the low resource language. And this is definitely one of the major limitations of the method.
Right. Yeah, because there are languages like the Euskadi, for example, that are these languages that are completely isolated historically and stuff.
Yes.
So it will be, I don't know, interesting to see what language would work with a process like this. And maybe and if it works, maybe we could say, well, maybe this is try to find the closer language to those strange and mythical language that nobody knows where they came from. So it's interesting. I really like your talk. Yeah,
that would be a really interesting problem, and hopefully someone will be able to solve that. That's a great question, and definitely one of the major things that we know that is a big limitation of our method.
Okay, thank you.
Thank you.
Anyone else question? I have a question. Nobody has. So currently in all the methods, we never utilize the knowledge structure. Like, so I don't know, I have read some papers which like do cross-lingual entity using GCN and like utilizing the structure in the knowledge base. Do you think like any of those ideas could be used here somehow? Because that part is totally right now, you are just using the text, unstructured raw text. So do you think that could be useful, or any thought about that?
That's again a really good question, and yes, it can definitely be useful. I do have a paper with one of my collaborators that basically uses the structure of English Wikipedia and the links within English Wikipedia to improve low resource entity linking. I did want to present that today, but unfortunately I didn't have time. But I'm happy to send you the paper, and you can take a look. And of course, that paper is not the end point of this research. There's a lot more exploration to be done, particularly in terms of using the structural information from Wikipedia, using the graph structure of Wikipedia, and so on. So yeah, that's a great question, and I definitely think it's important to explore that. But we haven't gotten the chance to fully explore that yet.
Thanks. It looked like your group has solved many of these problems, or are moving at least in direction of solving these important problems specifically. One last question, do you have any like open question suggestions or things which you think are challenging in this field, or people should look at it, or anything you want to say about this field?
Oh yeah, absolutely. So this is like entity linking for low resource is very far from being solved. A lot of the questions that you all have asked today, really point out some of the major limitations of the methods that I presented, including exploring graph-based methods, which have actually worked really well for high resource languages, but nobody has really done too much exploration on the low resource side. So that's definitely a good, that could be a good open problem to get into with this. And even in terms of candidate retrieval, although the methods that we presented do improve over existing methods, there is a lot of headroom for improvement still. The accuracies are still very low compared to high resource languages. So candidate retrieval in English, for example, is almost has like over 98% recall. And for low resource languages, we're barely at 60%. So, so yeah, there's still a lot of scope for improvement in all the parts of entity linking for low resource.
Thanks a lot. I'm sure at least few people will contact back to you because we are trying few things and definitely it relate to your group work and your work.
Oh,
So,
yeah, sure.
Yeah, thanks.
Feel free to email me anytime. I'm happy to take questions offline as well.
Yes.
And thank you everyone for attending.
Yeah, thanks for presenting. We cannot do a clap, but we can always do a virtual clap.
Sure.
So, and I will share you the video, although I'm a little disappointed less people join. But anyway, if the video will be there, I think people watch videos more these days, like at their convenience, at their routine, because routines are messed up because of the homestay kind of things. But anyway, I will send you that, and let us know if you have any feedback about us also.
Okay, I will.
And thanks for giving this talk, and I hope people enjoy. And thanks everybody for attending.
Yes, thank you so much. I had a really good time. Thanks, everyone.
Thanks.
Okay.
Thank you so much.
Thanks.
Thank you. Thank you. Bye.
Bye.